Thank you all for joining for this virtual presentation of landscape scale and aerial imagery approaches to finding fields, which I put together for the streaming event On Fields. My name is Madeline McLeester, and I've co-written this presentation with my Dartmouth colleague Jessie Casana. I'd like to acknowledge that I am recording this presentation in South Bend, Indiana, the home and ancestral lands of the Pokagon Band of Potawatomi. Our employer, Dartmouth College, stands on the ancestral and unceded lands of the Abenaki people. Let me begin by telling you a little about us. I first became interested in past Indigenous land use systems in Wisconsin while working on my dissertation. In that work, I used Huron Smith's ethnobotanical literatures to demonstrate how medicinal plant collection adds texture to anthropological understandings of gathering processes, and in particular, the ways in which religion, foodways, and medicine are intertwined. Relevant to today's audience, I calculated plant collection areas among historical Menominee medicine men and women that are 9 times the size of typical plant collection areas used by archaeologists. For the pandemic, I was scheduled to present these findings in person in April, but like so many pre-COVID plans, this talk was canceled. Nonetheless, I hope I'll be able to present it when it's safe to do so. Today, I'll be discussing a joint research project conducted in collaboration with my colleague, Jessie Casana, professor and chair of anthropology at Dartmouth. Jessie and I are interested in the ways that archaeological agricultural fields are embedded into complex social landscapes and how these spaces are composed of multiple cultural elements. We first paired up in 2017 to see if we could locate agricultural fields at a 17th century village in northern Illinois using thermal drone-based imagery. I've been excavating at this early pre-contact 17th century village since 2016 with my colleague Mark Schur at Notre Dame. The Middle Grant Creek site, featured on your left, is located at Medewa National Tallgrass Prairie, about 1 hour south of Chicago. We know the 17th century community practiced intensive agriculture because of the deep subterranean storage features that once held crops, namely maize, as well as a suite of agricultural tools, including an agricultural toolkit which was found all together. That included a mano and metate featured at the top, a bison scapula hoe in the center, a deer mandible on the lower left, and antlers. The deer mandible was possibly used as a corn sheller or a sickle, and the antler, given the context, was likely used as a rake. While Jessie and I did not locate any agricultural features in 2017, our thermal survey did find an earthen enclosure, a type of earthwork that is common at 16th to 17th century sites in northern Illinois. And through an analysis of historical aerial photographs taken in the 1930s, we also located possible house basins, providing us with the ability to create a schematic of the village, which is on the left. And on your right, you can see on the upper image, the earthen enclosure, which is visible in thermal imagery, and below that, different earthen enclosures and other earthworks, like the bison-shaped earthwork found in northern Illinois. Of course, what's missing from all these images are the agricultural fields. Undeterred, we began to think of other ways to investigate agricultural fields and determine how we might better identify them through aerial imagery. This past winter, we analyzed hundreds of historical photographs taken in the 1930s, as well as modern, publicly available LiDAR taken above archaeological sites at 59 locations in southwest Wisconsin where agricultural fields were recorded. Out of those 59 agricultural sites, we located cultural features at or near approximately 1/3 of them. Before we get into the findings, I'd like to note that it's important to recognize that historical indigenous agriculture took on a tremendous variety of forms. However, for this project, we were looking only at intensive maize agricultural field forms because they're the most likely field form to be visible in aerial imagery. Maize agriculture was conducted in 3 different field types: corn hills, ridged fields, and fields that were a combination of ridges and hills. So what did we find? Well, the first thing we found were things that looked very convincingly like agricultural fields. Those included haying, forestry tracks, and thumbprints. Fortunately, haying and forestry tracks were so abundant in nearly every image that we were quickly able to recognize them. Thumbprints, though, were especially challenging, since their curvature could really be very convincing. But because we analyzed multiple images from the same context, from the same location, we were able to rule them out as ridge fields. And you can see that thumbprint in C. Despite the hurdles, we did find things. As we suspected, ridge fields were the most common agricultural feature we could detect in these aerial images. Here, in an image from 1937 on your left, upper left, as well as in the LiDAR image taken in the past few years in your lower left, both of these images show ridges at Holbert Creek. And Bill Gartner's work at this site has established that the ridge fields at Holbert Creek are still intact. We also observed other cultural features, like the iconic mounds at the 118 Mound site. These are clearly visible in the 1930s imagery. And that image is on your left. Unfortunately, they were less visible in the LiDAR, suggesting that many of them have likely been destroyed or lost through erosion. While these mounds were exciting to find in the aerial image, we were looking for a field system that was recorded near these fields, which we did not observe. However, by taking a large-scale landscape approach, we observed what we believe is a previously unknown ridge field system about 1.5 kilometers northwest from the 118 mounds. Here, you can see the field in the historical aerial from the 1930s on your left, and next to it on the right, an image from the 1950s where forest growth now obscures the field. While the majority of the cultural features in our study have been destroyed, it's especially encouraging to see that this, a previously unknown field, showed up in LiDAR, which was taken in the last few years. So here you can see the LiDAR image on your left, and on the right, a satellite image from 2016. This tells us that the fields are probably still there, underneath the forest, and we're definitely hoping to get out there and ground truth them. And I hope you're also able to hear me over this blue jay who has joined our recording. So one big conclusion from this project of these historical aerial images was the ways that agricultural fields are embedded into expansive cultural landscapes. During our analysis of these aerial images, we were also able to locate several effigy mounds and other earthworks. For example, a bird effigy, a bear effigy, and a semicircle earthwork. We were also able to locate probable house basins. These house basins were again unrecorded, and while much of this area has since been developed, some of these house basins are located in sports fields. So a really awesome archaeological project for those looking for one would be to ground truth these house basins. These historical images are very important because they provide key information about agricultural spaces, like shape, possible dimensions, and how they are enmeshed with other cultural features. And many of them have since been destroyed, so these aerial images may be our only way to observe these fields. But these images were taken using 1930s technology, and they were not taken for archaeological purposes. That means that historical indigenous fields and other archaeological features were captured only by accident. So the next step is taking images of these agricultural features that are specifically designed to record, map, and analyze them, and hopefully we'll be able to include field systems within the Menominee Reservation. While this project is still in nascent stages, I want to talk about the geophysical methods we'll be using to help us record and map these field sites. First, we plan to collect thermal and multispectral images using unmanned aerial vehicles, also known as drones. In particular, we expect that fields and other features will be visible in these kinds of images, particularly in unforested areas, because of how they impact soil moisture, soil development, and plant growth. This was the case with the earthwork enclosure mentioned earlier that we located in northern Illinois. In these images from New Hampshire, Jesse and his team captured architectural foundations, most evident in the thermal images, the furthest image, or the second image from your left. But there were also some linear pathways and drain pipes visible, especially in the NDVI, or Normal Difference Vegetation Index, in the middle. In a contrasting example, Jesse and his team also undertook a small thermal survey at Cahokia, a Mississippian ceremonial center and city that needs no introduction. There, they focused on an area known as Ramey Field just east of Monk's Mound, where an earlier resistivity survey by Michael Hargrave had found several large rectangular structures. For thermal imaging, the challenge at Cahokia is dense vegetation, which creates a lot of noise in thermal data because of the water retention and transpiration of plants. Thermal imagery at Cahokia was hard, and most of the data did not align properly due to the relatively homogeneous unmowed grasses. In the mowed area, where mowing lines show up as bright stripes, we can see a few features, but none of the big buildings previously detected. Instead, we see a few east-west oriented linear features, which prove to be 19th century field boundaries. In addition, the older excavations in this area also appear with clarity. However, neither fields nor excavations show up in resistivity data, showing that thermal imaging, even if less than perfect, can be a useful complementary geophysical dataset. In addition to thermal and multispectral imagery, we'll also be conducting drone-based LiDAR over the fields, because LiDAR works well in more heavily vegetated landscapes. In our findings from Wisconsin, as previously mentioned, fields are visible in several examples using publicly available LiDAR. And the fact that some ridge fields are resolvable in 1 meter public LiDAR data suggests that we'll be able to see them even better in drone LiDAR, as it offers around 25 times the resolution. The displayed image is the LiDAR from Mesa Verde, where house compounds and irrigation features are visible in the bare earth model, which is at the bottom of this slide. There are obviously differences between the sorts of features we're looking for within agricultural fields, but this example is similar in that they have a comparable topographic expression to the irrigation features. And last, in addition to drone-acquired images, we'll also be conducting on-the-ground magnetometry. Magnetometry can detect subterranean features like storage features, which may be contained within the agricultural fields. In the above images from the Kurdistan region of Iraq, the Sparkle Lab at Dartmouth located courtyards and buried mud brick. The best advantages to these geophysical methods is that they are non-destructive and can cover a large area fairly quickly. Therefore, our hope is that this upcoming project will provide complementary data sets to ongoing research on historical indigenous agricultural fields in Wisconsin, including the great work by David Overstreet and individuals at the College of the Menominee Nation. These complementary data sets will help advance our understandings of past indigenous agricultural practices by providing details on the shape, size, and related cultural features of archaeological agricultural fields. And with that, I would just like to say thank you.